So now let's talk about the function that does tell you if a reaction is spontaneous or not. That function is, or that state function, if you will, is the change in Gibbs free energy, or the change in Gibbs free energy of reaction under standard conditions, although we will also be at non-standard conditions as well. And let's just start right off. If delta G naught reaction is negative, then the reaction is spontaneous. Now, let's start with the one equation for delta G. Delta G naught reaction equals delta H naught reaction minus T delta S. And T delta S naught reaction. So this is temperature. Temperature has to be in Kelvin. T in Kelvin. And this equation is also true at constant temperature and pressure. And if you remember, delta H was at constant pressure. And it doesn't mean that we can't change temperature. It means, though, that the value of delta G is specifically at this temperature. Okay? Now, what this does is this combines two trends. So if delta H is negative, that means the reaction is exothermic, and that tends to be spontaneous. And we said if delta S is positive, that tends to be spontaneous as well. Put the minus sign in there, and it combines the two trends. And it actually gives us four possibilities. And what we'll do is we'll set up a little table, and we'll look at, let's see, delta H, delta S, and delta G. And we'll say, and then, oh, I don't know how we're going to do this, but let's see. Oh. We'll call this number 1, and we'll say, we'll look at the case of if delta H is negative, which means it's exothermic. We'll look at the case if delta S is positive, and that means matter is more dispersed. And so the plus for delta S, since T is in Kelvin, T is always positive. Positive times a positive is always positive. Put in the minus sign. This whole term becomes negative, and delta G must be negative. And if delta G must be negative, that means that the reaction is spontaneous, as we will see. And not only is it spontaneous, it is spontaneous at all T. Because T could have any value from 0 to infinity. Not that that's legal or legit, but if this is negative and this is positive, delta G will always be negative, and the reaction will always be spontaneous. All right, so let's do number 2 now. Number 2 is going to be positive delta H, which is endothermic, and positive delta S, which means matter is still more dispersed. And what we can say is, well, if this is positive and this is positive, there is some temperature, we don't know what it is, but above that temperature, delta G will be negative. So let's say this. Delta G could be positive or negative, but let's say delta G less than 0 at high T, which means reaction is spontaneous at high temperature. And there are two more cases, and I will let you fill them in, and you will see those cases again. But the reaction can be spontaneous at low temperature, and the reaction can be spontaneous at no temperatures, which is another way of saying that the reaction is always non-spontaneous. Okay. Now, so that's the first thing is if we look at different temperatures and the signs of delta H and delta S, we can tell when and at what temperature a reaction will be spontaneous. Now, more about delta G. So, and I'll just state this right now. If delta G is less than 0, whether it's delta G naught, what have you, delta G naught reaction, the reaction is spontaneous. And that's why we calculate delta G, the Gibbs free energy. 2, delta G naught, whatever delta G it is greater than 0, reaction is non-spontaneous. Which means the reaction does not occur. And further, if the reaction is non-spontaneous, so reaction does not occur in the forward direction, semicolon, reaction is, so delta G will change signs when you reverse the reaction, just like delta H. And another thing we can say is that the reverse reaction has delta G naught reaction less than 0. And is spontaneous. So that's another thing we can say, and we'll talk more about that. 3, if delta G equals 0, the reaction is at equilibrium. The reaction is at equilibrium. All right, we have more to say about delta G. The next thing I want to say is that we will use at least two different methods. There is actually many ways to calculate delta G, but we'll start with the two most fundamental. So this is going to be 4. This is on the second page that you've got. You can calculate delta G in the same way that you calculate delta H, meaning you sum the products and you do coefficients and you look up the change in free energy of formation under standard conditions of the products. Do the same thing and subtract off the reactants. And the values for delta G of formation are tabulated right next to the delta H and the S values on your conversion and equation sheet. Now, we will many times be interested in finding out the temperature at which a reaction, so if there's a temperature, and if so, what that temperature is at which it changes from spontaneous to non-spontaneous. So we will first calculate delta H and delta S, and then solve for temperatures as well. And so this equation allows you to determine the temperature dependence of delta G. Okay. And so we'll use both of those depending upon the situation. And then finally, let me just say, let's talk about what delta G is. It's called the free energy, and specifically the Gibbs free energy. And so now, what is the Gibbs free energy? And we'll come back. Actually, I guess we can use this version of the equation right here. You can see it's equal to the heat energy of the reaction when you take away the entropy term times temperature. So what we can say is the Gibbs free energy is the heat energy available to do work. What's this? It's the heat energy taken away the heat energy that has been used to increase the dispersal of matter. So heat energy of reaction with the, so heat energy of reaction minus the increase in entropy. Or dispersal of matter. So that's one definition. I'm not sure if that helps at all. The heat energy minus the increase in entropy, and there's a temperature factor in there. Now, think of the heat energy as the energy that can do work. So the heat energy is the energy that can do work, except that some of that energy is used up to disperse matter. So when you subtract this part off, what's left, and what's called the free energy, is the energy that's available to do work. So the heat energy, delta H naught reaction, we can think of it as the heat energy that could do work, except that matter is dispersed minus T delta S. So delta G, which is the free energy, is the free energy available to do work. And so that's what we mean by free energy. It is the energy that is free to do work, that is available to do work after dispersing matter. Now, let's do some examples where we calculate delta G reaction. Oh, I think I already did, so let's actually stop there, because calculating delta G were the notes that were right here.